All right, let's talk about what's going on, where we're headed here. First of all, please check your email. I sent an email today that is not a review, okay? It's not a review for the final. It's actually some problems that I used on the final last year, a year ago, last fall. So it's a study guide. And the email does state that you should, like I've said, review your homework, review your old exams, but it gives you some sense of where I was pulling problems from. And we'll talk more about that final on Thursday, but at least you can, get a little head start on it, take a look at it. Our final is a week from, well, it's Thursday, so a week from this Thursday. It starts at 12:30. That's not my decision, that's the way it's been set since day one. So even though class starts at 1, our final's supposed to start at 12:30. And it goes to 3:15. And it's right here. Okay? Today we're going to do more antiderivatives or integration. And Thursday we're also going to do more antiderivatives. We're going to talk about something called the evaluation theorem. And we'll talk about the final a little bit. I'm hoping that you'll have some questions. You'll look at that thing I sent out and maybe have some questions like, hey, are you really going to ask us to do limits like this? Like pick my brain a little bit about what's going to be on the final rather than me just coming up here and telling you what's going to be on a final that I haven't written. Okay? Because I probably won't write that final till this weekend. Or maybe 10 minutes before class. 10 minutes at 12:20 I'll write the final. Yeah.
Sounds good. He's like, well, I found these problems on the Google. You got it.
Yeah, I just Googled it. I looked at Cliff Notes. Okay, so formula sheets. Well, yeah, I guess that's it. Any questions on this?
Formula sheet.
All right, so I put that up there so I wouldn't forget. All right, what we talked about last time was we were trying to find antiderivatives, right? And we use this new notation that basically says that if you're asked to find the antiderivative of some function, little f of x, that's the notation that we use. Right? We call this, y'all remember? The integral sign. And then this dx, I told you that it was important because it keeps track of what your variable is. And really, the dx for us here, I could have written as a 1. Because if I ask you, like, what's the derivative of x with respect to x, you would just say 1, right? dx is 1. But this little differential out here is not always 1. I did an example last class where I did a substitution, and people were like, what the heck? And it turns out that is very important. So we call this the differential. So we're going to do more of this. But on your formula sheets that I provide you and you're allowed to bring on the test, and by the way, this is also the same exact formula sheets that I allow my Cal 2 classes to use. All right, so the same 6 pages. We already know that there's an entire page here for differentiation. Has all the derivatives, product rule, quotient rule, chain rule, power rule, derivatives of exponentials and logs, derivatives of all the trig functions, derivatives of all the inverse trig functions, derivative of all the hyperbolic trig functions, which we did not talk about, and all the derivatives of the inverse hyperbolic trig functions, which again we did not talk about. But in Cal 2 we'll knock those out right in the beginning of class. That's what we do. Knock out the hyperbolics. And so this is pretty much like Cal 1 derivatives all wrapped up on one page. But when you get to Cal 2, we're trying to do antiderivatives, so the next formula sheet has all these integral signs, right? And what I wanted to point out was that this has a lot of information on it, all right? This has, first of all, this first rule, this first form, just ignore it, okay? That's actually an entire section in the book. This is what we call the integration by parts formula. So that, ignore. The second formula, that should look familiar. Do you remember we came up with a formula last time? If you're trying to find the antiderivative of x to the n, Do you remember? X to the n. All right, this was the formula that we came up with in class. We did something like this, though. We said that the antiderivative of x to the n would actually be two different things. Do y'all remember me doing that?
Yes.
It was, I put 1 over n plus 1, x to the n plus 1, and then over here I put natural log of x, didn't I? And this is if n was not negative 1, and this is if n was negative 1. Plus c on both of these, all right? And there's also one additional thing that, well, I'll point it out in a second, but this is the same, this right here is the same formula as this one, except they're using u instead of x, all right? They're using u instead of x, and since 1 over n plus 1 is a constant, you could just slide the n plus 1 underneath this entire thing, which is what they've done here. Do y'all see that? Okay, so that's the same formula, and they say as long as n is not negative 1. Now what if n is negative 1? Well, that's this. That's the third formula. This right here, the way they wrote that, integral, I'm going to do it in terms of x, dx over x is the same as integral 1 over x dx. Do y'all see that that's the same thing? Just sliding the dx out to the side. And this right here is x to the negative 1 dx, and that's the special one. So that's what we're saying here. Y'all following me? Yeah. Okay. So there's a plethora. You don't get to use that word very often. There's a plethora of information on this page. You'll want to memorize those at some point and not need the reference page, but just for the final, just know you're going to have this. All right? The antiderivative of e to the x, I'm going to say x instead of u, all right? The antiderivative of e to the x dx would just be itself plus a constant. This one's a little tricky. The antiderivative of a to the x. The antiderivative of a to the x dx. You have to go back and remember what was the derivative of a to the x. So do y'all remember what the derivative of a to the x is? If a is a constant? It's itself, and then we had to throw something right here. Natural log of a, right? Natural log of the base. So if I say the antiderivative of this is itself, I'm going to be off. Right? If I just say this, that's going to be wrong because the derivative of this is not that. It has this natural log of a there also. So I don't want that there, do I? So I divide it out. So that's why they have a natural log of a down here. Do y'all see that that divides out? That natural log of a that would pop out?
Yes.
Okay, thank you. A response would be great. Okay, a to the u plus c. That's the same. This is the same as this. So 1 over natural log of a is just a number. All right? If I say take derivative of this, you're going to say it's itself times natural log of a, but then this 1 over natural log of a kills it off, and you get just the a to the u. All right, and then the next few are pretty, I would say, easy as long as you know what the derivative of sine and cosine are. So the antiderivative of sine is negative cosine. Because remember, the derivative of cosine is negative sine, so you want positive sine here, right? So you have to put a negative in front. Now the antiderivative of cosine, fortunately, that's just sine. And then we have to make our integrals very special in order to get back to like the other common trig functions. Right? Like the antiderivative of secant squared, I know that that's tangent because I know the derivative of tangent is secant squared, right? But what's the antiderivative of secant? Good question, right? Oh, there it is. It's natural log of secant u plus tangent u. Whoa, where did that come from, right? So that's not a very easy thing to see, and in Cal 2 we'll explain where that comes from.
Is that absolute value?
Yeah, I told you I was going to point it out, forgot to point it out. From here on out, if you do the antiderivative of 1 over u or 1 over x, the antiderivative is natural log of the absolute value of x. And that's because the natural log function is not defined for negative numbers. So we put the absolute value there to make sure that it's defined. All right? What else? If I can take the antiderivative of secant squared, that gave me tangent. There's some other ones I should be able to get also, like cosecant squared u. I should be able to do the antiderivative of that because I know the derivative of cotangent of u should be negative cosecant squared u. This is my knowledge of the derivatives of the 6 trig functions. And so if I slap a negative on it, it's going to make this positive. We all know derivative of secant is secant tangent, right? So I can go backwards from secant tangent back to secant. So I'd say numbers 2 through 10 are all things we should be somewhat familiar with. Then when we get over here, let's see, number 11 is also one that you should be somewhat familiar with because you should know that the derivative of cosecant u is negative cosecant u cotangent u. And so you slap a negative on this and that would make that positive. Following? Okay. Once we get to 12 and on, these are things that are not familiar to us at all. And they look nasty, don't they?
So it's number 20.
And then you get to like 21, 22, 23, 24. These look really bad, don't they?
We're just supposed to know this.
No, you're not going to memorize these. We're going to have a technique. We're going to have a technique that we can use to attack each of these. But all of these have a certain form. Notice all of these on this sheet involve a square root of a squared plus u squared. If you ever have integrals that involve this expression, here's some like cookie cutter formulas that we have for them. But we can actually come up with all these formulas on our own. And then we get down to 29 formulas and that's it, right? That's it, that's Cal 2, no. So I stop at page 6, right? But the book actually has another reference, page 7, which goes to formula 46, reference page 8, which goes to formula 62, and then reference page 9 that goes to formula 95, and then they stop at reference page 10. There's 120 integral formulas. Now we won't use these, all right? There's actually a section in the book in Cal 2 where we say, hey, look, see that table back there? Let's practice using that table. But the problem they give you has to fit into one of these forms. Like it has to perfectly match in to be able to use the table. So we just like kind of wave our hands at it and go, look, those formulas are there, but we want to be able to try and do these integrals by hand without going to the formulas. Because even though there's 120 there, you can find reference books like in the library, maybe not this library, but like at a major university, that is just a table of integrals, hundreds of pages of formulas for integrals, right? So there's no way you want to memorize any, 120 or even 1,000 formulas. It's more important to have a technique to attack them. So in Cal 2, what we do is we spend a lot of time on what we call the techniques of integration. How do we integrate? All right? But just know that these formulas are here, at least these first 12 or so, taking out that first one, the first 11. All right? So let's get warmed up here. We're not going to do the substitution, right? That's kind of what we ended class with last time. I want to hold off on that. I'm going to go back to the substitution after we do some more just regular antiderivatives. Right now, as it stands, we can only do antiderivatives of x to powers, right? X to different powers, or it's got to fall into something I already know, like the antiderivative of cosine. Other than that, we're going to act like we don't know what to do, all right? So let's try this one. What's the antiderivative of x cubed minus 3x plus root x squared dx? So you sit there and you go, okay, well, I know that individually, these three, I should be able to find the antiderivative of each one of them separately, because this is x to a power, that's x to a power, that's x to a power, right? However, the whole quantity is being squared. So you are not allowed to just do antiderivative, 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 and then just like square that answer. You actually have to square this out first. That's your only option right now. You have to actually FOIL this out before you find the antiderivative. All right? So I'm going to do that. This is just algebra. I'm going to do that over here. I'm going to do x cubed minus 3x plus root x times itself, x cubed minus 3x plus root x. And then we get to do, it's not FOIL, right? This isn't technically FOIL. It's called expansion. Thank you. Very good. X cubed times x cubed. X to the sixth. Okay, this is going to get a little weird. So I'm doing that times that. Now this times this. I'm going to get negative 3. I'm doing x cubed times x, which is x to the fourth, right? And then this last multiplication here, that one's going to be a little weird. This is x to the half, right? X to the 1/2. So x to the third times x to the half, you add 7 halves. 3 plus a half is 7 halves. Okay? One thing you don't want to do, all right, is you don't want to write this as 3.5. Even though it is. This is a mixed number, and we no longer use mixed numbers. They're not made for calculus. Because remember when you bring numbers out, like when you do power rule, you bring the number down, subtract 1. These don't work that well for that. So we need to be able to get common denominators. So we add this together at 7 halves. So this is going to be plus, right? Plus x to the 7 halves. All right, now what? I've done this one through to each one. Now, this one through to each one. I'm going to have a total of 9 multiplications here. So what is negative 3x times x cubed? Negative 3x to the fourth, right? What's negative 3x times negative 3x? Positive 9x squared. And then the next one, this is negative 3, and then this is a plus, so I'm going to put negative 3. X to the first power times x to the 1/2. 3 halves. And I keep going. What's root x times x cubed? X to the 7 halves again, right? I'm going to continue down here because I don't want to go off screen here. So plus x to the 7 halves. And then I'm going to do this one times this one. That's going to be a minus 3 x to the 1. It's 1/2 plus 1 again, right? So 3 halves again. And last one, root x times root x. Just x. Okay, now collect like terms. I have x to the 6th, so I've taken care of that. It doesn't matter what order we go in here. How about minus 3x to the 4th minus 3x to the 4th? That's going to be minus 6x to the 4th. So I've taken care of those. Let's take care of all the easy ones. 9x squared. Taking care of that. I have just an x by itself, so plus x. Taking care of that. And now how about these weirder ones? X to the 7 halves. I have one of them right here. I have one of them right here, so that's 2 of them, right? So I have 2x to the 7 halves. And I've taken care of these. And finally, minus 6x to the 3 halves. I haven't done any calculus yet, right? It's just algebra. So I'm going to come back to this now. I'm going to say what I'm really trying to do is find the antiderivative of x to the 6th minus 6x to the 4th plus 9x squared plus x plus 2x to the 7 halves minus 6x to the 3 halves. I close the parentheses and I say dx. Now I'm going to use the power rule on each one of those. So let's see if we can do this. When I actually apply the power rule, right, for antiderivatives, there's going to be no more integral sign, right? This dx is going to go away. I'm just going to write the antiderivatives of each term and then plus c at the end. So what is the antiderivative of x to the 6th? 1/7 x to the 7th. So I was curious before I came into class today whether or not y'all were going to be able to recall us doing that quickly or not. Is that all right for the first one? All right, what about this negative 6x to the 4th? I can cover up the negative 6, right, and just bring it with me because it's a constant. So what is the antiderivative of x to the 4th? 1/5 x to the 5th, right? But then multiply that times negative 6. So negative 6/5 or negative 6 over 5. X to the 5th. Do y'all see that? You have the negative 6 out here. It multiplied times the 1/5 that comes out when you take this antiderivative. Antiderivative of that is 1/5 x to the 5th. Then you hit it with the negative 6. It's negative 6/5. Is that too much or is that okay? All right. What about the next one? 3x cubed. Because it's 9 times 1/3 x to the 3rd, right? So the 9 times 1/3 is the same as 9 divided by 3 is just 3. X cubed. And can't you always just, no. Yes. No. Hold on. 3rd? Yeah. Yeah, sorry, having brain fart. When you bring if you took the derivative real quick, 3 times 3 would give you 9. And then you reduce the power and that would be x squared. All right, how about this one? 1/2 x squared. Good. This one might be a little bit of work. Let me just write it down up here. I'm going to do 2 times. Okay, tell me about that power. I've got to add 1 to 7 halves. 9 halves, right? So this is going to be x to 9 halves. And then I'm supposed to put 1 over the 9 halves, right? That's the power rule in action there. But 1 over 9 halves is always going to be just the reciprocal of 9 halves, which is 2/9, right? So this is really going to become 2 times 2 over 9, x to the 9 over 2. That's a 9. And what's 2 times 9 or 2 times 2/9? 4/9. 4/9. So this becomes plus 4/9 x to the 9 halves. And again, we could check it real quick. If I bring the 9 halves out and hit that, right? 4/9 times 9 halves, the 9s would cancel, right? The 4 over 2 would become 2. So that would give me the 2 right there. All right, how about this one? I'll do that one the same way I'll do it up here. I have negative 6 there, times I'm going to leave a space, x to the what power? 5 over 2. Then I'm supposed to put 1 over 5 over 2 here, right? Which is really 2 over 5. And so look, y'all notice the pattern here? If this is a fraction, right? Then the number out front of it's always going to be its reciprocal. And multiply that, you get negative 12/5. So negative 12/5 x to the 5 halves. Am I done? Plus c. So on your exam, your final, I'm going to expect that if I gave you this line, that you could get to here, all right? I want you to show me that you understand power rule for antiderivatives. This thing with expanding, I may not ask you to expand this. What I wanted to illustrate in class was that, look, we can handle this still. It's not pretty, but we can do it. Now, what if this was changed to like 20 instead? Could we do it theoretically? Yes, if you wanted to spend the next week multiplying that out 20 times, right? It could be done.
Is there any shortcuts?
In this one, I don't see a shortcut. Even if you finished Cal 2, I don't think you could do that easily. I mean, I know you couldn't do that easily. There's not a shortcut for that, unfortunately.
Not really a shortcut.
Not for that one. Nope. Not for that one. Well, the computer. The computer, yeah. All right. We good? Yes? All right, now we're going to talk about something else. If I start with the function f, right? If I differentiate it, Cal 1, right? I know we're still in Cal 1, but this concept of differentiation is a Cal 1 topic. I get its first derivative, right? F prime. And if I differentiate the derivative, that means I take a second derivative, then I get f double prime, right? All right. Now let's say we try and go backwards. Let's say I started at f double prime and I go backwards. This is integration. I'm just going to put int. I would go back, right? If I were to go from here, if someone gave me the second derivative of a function and asked me to produce its first derivative, right? You could almost, right? What's going to happen when you try and go backwards? You'll get a function, but what are you going to always have to have in there? Plus c, right? And that means you're going to be off a little bit, aren't you? You're going to have it within a family of functions, but you're going to be off by some constant. So when we go back here, we'll get f prime plus c. Now, can we get back to f from f prime?
No.
Not really, because
Sometimes, but not usually not.
if we don't know what that constant is, right? It could be any constant. Then when we try and go back, this function f is going to be, not only are we going to have a constant because we integrate it again, but there was a constant here which we would have to integrate to. So this is going to be kind of weird, isn't it? Trying to go back? It's kind of a question. Can we get back to f? I'm trying to get us to think about this. Can we actually recover that?
Because if that constant after the differentiation was an x, like let's say if it was like 3x, and then we differentiate it, that's just a 3 now.
Yes.
So then we would know if that was an x or just a constant.
That's right. We don't really know what it came from, right? We know that when you're standing over here, potentially, think about it this way. If there was an x squared anywhere in this function, are you going to see it over here? The first derivative is going to give you what? 2x, and the next one is going to be a 2, right? Well, I guess you see it there, right? It would be a 2. It would be easy to go back.
Yeah, but we still
Yeah?
wouldn't know.
Yeah, let me do it this way. Forget x squared. Let's just say 5x. Would you see that over here? No, because you take the first derivative, what would you get? 5, and the second derivative, you would get 0. It wouldn't be there, right? So there, I mean, you could have any linear expression over there that you're not going to be able to see. So, all right. Do you understand there's a little bit of a problem going backwards? And it's the plus c thing that happens. When we differentiate, there's no problems at all. There is only one function that can be the derivative of this. When you differentiate that, there's only one answer. We differentiate that, there's only one answer. We try and go backwards, there's an infinite number of answers. Go backwards again, there's an infinite number of answers. So there's some trouble. Another way to illustrate it, I showed y'all last time that formula. I think I wrote d of t was negative 16 t squared plus v naught t plus d naught, right? And we talked about objects falling on Earth, right? And that this formula represents that. And that this comes from the idea that if you have the distance function, you take its derivative, you get the velocity function, You take the derivative again, you get the acceleration function. So if this is our position function, what's the velocity function? The derivative of that, which would be what? Negative 32t plus v naught. Because this right here is like, let's just say it's like 5t. What's the derivative of 5t? 5. So that would be this. And then that's a constant. Derivative of that? 0. It's gone. Then if you differentiate again, what do you get? Negative 30. Wait, hold on. This should have been t. Sorry. This would just be negative 32, right? It's just a constant. And this is what I was saying was the acceleration of gravity. So if you look at it this way, this is what I was trying to get you to think about. If I tell you the acceleration of gravity is negative 32 feet per second per second, if I tell you that, do you think you're going to be able to tell me exactly where an object is at every point in time? No. Right? If I give you acceleration, the acceleration of an object, there's no way from that alone you will be able to tell me its position at every point in time. Impossible. But how much information would we need to actually go backwards? So that's what the next example is all about. What's the minimum amount of information we need to go from here all the way back to here? And it turns out you don't need much. You don't need much at all. So let's try this. Let's say I tell you, you're given here that f double prime of x is 24x minus 6. And I'm going to steal this problem from my Cal 2 lecture, so hold on. Is it this one? Yeah. S1 is 7, F2 is 41. Hold on, did I have prime on that or not? Seven and 241. All right, you're given all this information. So I've given you the second derivative, exactly what the function is. I've given you the value of the original function f at 1. If you plug 1 into this function f, you get 7. I've also given you one other piece of information, the value of the derivative, the first derivative, at a single point. So if you want to, you could look at it this way. Visually, you could look at it this way. I've given you f double prime is 24x minus 6 is a line, isn't it? Right? Yes. What do you mean? This is given to you, right? This is the function 24x minus 6. All right? That's this line. I'm telling you that's the second derivative. I've also given you some information about its first derivative. The only thing I've told you is that at 2, what? It's 41. So I've given you a single point on the first derivative. That's it, right? That's what I've given you. And I've given you one other thing. The original function at 1 at 7. Right? So I've given you the second derivative completely, given you one piece of information about its first derivative, and one piece of information about the original function. Can we from this recover what f is exactly? The answer is yes. Let's do it though. All right? So the instructions here, find f. Don't understand? Do you think that's enough information? Yeah, let's see. Let's see if it is. Yes, the answer is yes, but what it's going to turn out to be, what we're asking for here, is I want the exact function. Whatever this is, I want it. Tell me what it is. that will draw that red function. And I drew it like a cubic function. Why do you think I drew it like a cubic function? This is linear, right? So I've got to go back once, it's going to turn that to x squared, and I go back again, it's going to go to x cubed. So I already know that that's going to be a cubic function. But I want to know exactly what it is. All right, so let's start with this. Do you agree with the following? Do you agree that the first derivative, f prime of x, should be equal to the antiderivative of the second derivative of that? Does that make sense? Right? The antiderivative of the second derivative should be the first derivative. So what is that? Well, that was given to us, 24x minus 6, right? Can you find the antiderivative of 24x minus 6? 12x squared? 12x squared. What else? Minus 6x. What else? Plus c. You cannot forget the c. All right? So look, we know, kind of, what the first derivative is, right? We know it, but we're off by a constant. You know it? Okay, how'd you get it from here?
You plug in the 2 to the x's, so you get 12 times 4, that's 2 squared.
Yeah, so look, this information is going to say, hey, look, when you plug 2 in for x, your derivative, first derivative, needs to spit out 41. So I'm going to use that information right now to try and nail down what c is.
So you plug 2 through there, then you figure out what your constant needs to be.
That's right. So I'm going to put, but f prime of 2 must be 41, so 12 times 2 squared minus 6 times 2 plus c must be 41. Do you see how what I'm doing is I'm plugging in 2 for all the x's? That must result in 41. If you look at that, that only has one unknown in it, right? C? So this is going to be 48 here, minus 12 plus c must be 41. 48 minus 12. I can't do it. Why don't I do what? I'm trying to solve for c. So that's 36, and then subtract, so you get 5. Yes, you probably said that already. Sorry. So c is 5. Hey, so I know what c is. I have nailed down exactly what f prime has to be for this to work. So f prime of x is exactly 12x squared minus 6x plus 5. Now, I'm halfway there, right? I've discovered what f prime is. Now I've got to go back and find f, but I've got the same thing working for me, don't I? I have another piece of information about f that's going to allow me to nail down the constant I get when I get to there, right? Okay, let's do it. So f of x should be the antiderivative, right, of the derivative, the first derivative, which is the antiderivative of 12x squared minus 6x plus 5 dx. And that is 4x cubed, right, minus 3x squared plus 5x plus a constant. Now, my advice to you is to not call this one c, only because we already used c in this problem. C was something else, wasn't it? So I'm going to use a different letter for a constant. I'm going to use capital D instead, and that's what the book will do also. Sometimes they'll do it this way, C1 and C2, depending on the book. Like C1 was that first constant, C2 is this second constant. But you need to distinguish the two. Okay? So this is what f of x is. We're off by a constant. But, what can I say? But f of 1 is 7. F of 1 is 7. So we get 4 times 1 cubed. 1's easy to plug in, right? Zero's even easier, but they didn't give us any information about that. That must be 7. 4 minus 3 plus 5, 6. Subtract 6 on both sides, D is 1. And now you'll have what f of x is. So f of x is this, 4x cubed minus 3x squared plus 5x plus d, but d was 1. And that is my final answer right there. So wow, it turns out that if someone gives you the second derivative of a function and wants you to go back to the original function, you just need one point on the first derivative and 1 point on the original function, and you will be there, right? You'll get it. If you were to turn this into the acceleration, when I said, if you drop something on Earth, are you going to be able to tell me exactly where it was? No, but if you tell me the speed of the object at any point in time, just give me 1 point in time, measure its speed at 1 point in time, and then just tell me at 1 point in time where it was, I will be able to tell you where it was all the time. Yeah? That's what we just determined. Yes?
So when going back to the original function of f,
Uh-huh.
can we actually pick arbitrary points for the antiderivative to find the next antiderivative?
What do you mean?
Because the constant is just the plus b on the y-axis. Like, because the function's going to look the same.
Yeah, they all have the same.
Constant is, so I guess my question is, could you pick just an arbitrary point
Off of what though?
off of the antiderivative? Like, once you find the antiderivative of the
Like, are you saying before we find the constant or after we found the constant?
I mean, excuse me, I got it backwards. The derivative of the antiderivative.
The derivative.
Like you have f prime 2.
Uh-huh.
You have f prime 2.
Yes.
You want to find f prime 1, the function, could you just pick some arbitrary point?
Oh, absolutely. Once you have what this is, once you have this, now look, if you want to know the speed of this object at any point in time, I've got it. Right? This is it. Now that's what we're talking. That's if the second derivative was acceleration, and the first derivative was velocity, then yes. Once you recover this function, once you have it, and there's no more plus c, then now you can tell me anything about its velocity at any point in time. So I guess I should add that to what I was saying. If you know the acceleration of something at every point in time, then if someone supplies you with just its velocity at a single point and its position at a single point, you will be able to tell me exactly its position at every point in time and, if you'd like, its speed at every point in time and its acceleration at every point in time, but you already knew that. That was already given. Is that kind of what you're saying? I don't know if that's what you're saying.
Does something have to be given?
Yes. Yes. Because when this was a plus c, right? Let's act like they didn't give us anything. How are you going to get a point on your own? You don't, even if you plug a value in, plug anything you want in here, right? You're still going to not know what that is. So you're not going to know what the output is.
Yeah, okay.
All right, let me try something. Now I'm gonna take the same problem we just had, all right? And I have not worked this problem out, so I'm hoping that this is not going to become a disaster, but it has potential to become a disaster. All right, f double prime of x is equal to, what was it, 24x minus 6? All right, what if I give you that f of 1 is 7? That's the same thing I gave you earlier, right? But instead of telling you that f prime of 2 is 41, I'm going to tell you that f of 2 is 41. Ooh, that's different. That's very different, isn't it? In terms of a picture, here's what I'm doing. I'm saying, look, I know what the second derivative looks like, right? That's given to me. In terms of the first derivative, I'm not given anything, right? Nothing. But in terms of the original function, what am I given? 2 points. At 1, I'm at 7. And at 2, I'm at 41. I know that's not drawn to scale, but... No, well, we know that this is a cubic function, don't we? But it's got to go through these 2 points somehow. What is that cubic function? You think we can get it? Do you think without having any information about the velocity and 2 pieces of information about its position, that I'll be able to recover its position completely? And also its velocity at every point in time.
What's the professor fancy?
What do you think? I mean, what does your instinct tell you?
My instinct says no. Because
No?
if you have a constant out there, that's great, but what if that constant is a variable? We wouldn't know if that was a variable in the first function.
No?
Could you set those 2 points equal to each other? The first derivative? I mean, the original function?
We don't know what the original.
Yeah, we don't know what it is. That's what we're trying to do. We're trying to find what f is. We're trying to find this purple function, right? All I know is that it has to go through those 2 points and that this is its second derivative. I want to rephrase this back in terms of the object falling on Earth, because I think it's more profound if you think about it this way. If I drop something on Earth, tell you the acceleration of gravity is the only force on it, right? Then can you tell me where it is at every point in time? We already said no. No way, right? We just learned that if you tell me its speed at one point in time and its position at one point in time, we can find out exactly where it is, right? This question is saying, all right, you got an object dropping on Earth, let's say. Can you recover exactly where it was at every point in time by just telling me where it was at 2 points in time, its position at 2 points in time? Whatever your instinct is whatever your instinct is. The answer is yes, we can do it. But let's see how it's going to work, all right? Let's just see how it's going to work. Can you all kind of tell that when we get to that first integration and get that plus c, that there's nothing we're going to be able to do to nail it down? Okay, so let's do it. Bless you. We know that f prime of x is equal to the whoa, I almost did a double integral. That's Cal 3, sorry. 24x minus 6 dx. We'll just start with triple integrals.
It's no big deal.
All right, so we know this, right? Pardon? What about the mean value theorem?
I'm looking at it.
Mm-hmm. I know it's your, yes, but that will give you, okay. All the mean value theorem would say is that you got these 2 points, right? And that they're connected by some thing like that. We don't even know what that is. That there's basically a place where the derivative is parallel to that, but that to the secant line, right? So, you know what? Maybe, but I think that's going to be a lot harder than this. And even with the mean value theorem, don't you need the derivative of the original function?
Yeah, we don't know what that is.
We don't, well, we do, but we're going to be within a constant. And that's the problem. We're going to be within a constant the whole time. Let's just grind this out. Sometimes in math, you just got to work it out and see what happens. All right, so I know that f prime of x, we already did this, was 12x squared minus 6x plus some constant I don't know, right? Some constant I don't know. Oh, well, okay. That's what it is. Then the original function should be the antiderivative of this, yeah? So let's do the antiderivative again. And yes, I'm going to have to take the antiderivative of c.
How does that work?
Well, it's just a constant, right? So let's say it was 5, then the antiderivative would be 5x, wouldn't it? So the antiderivative of c is going to be cx. Yeah? So this should be, we just did this, is this right? 3. So 4x cubed,
Hold on.
wait a minute.
No, it's
No,
negative.
I screwed this up. What the hell? Is this right? Was that the original function? Yes. And then antiderivative here, 2 and 6x. And I just don't remember.
It is.
It just seems like it looks different to me. 3x squared, right? Plus cx plus some constant. And do you see why it's important to use d and not c? Because these aren't the same numbers necessarily.
Could we, if we write it as C1 and C2, that's fine.
That's fine also. Yep, you can write it as c1 and c2 if you'd like. Everybody good? Sure? That's what f is. I still don't know what f is, do I? I know it, but I still need to figure out what c and d are. However, but f of 1 is 7, which means if I plug 1 into this, it should spit out 7. Let's try that. Plug 1 in right here. What do you get? I'll actually write it out. 4 times 1 cubed minus 3 times 1 squared plus c times 1, right? Plus d, that must equal 7. So what's that? 4 minus 3, 1. And c plus d, well, I don't know. C plus d is 6. Isn't that what that says? What is this, 1? Subtract 1 on both sides. You get c plus d is 6.
Yeah.
This is going to become a system of equations.
As soon as you,
Right.
as soon as you,
to each other, I think.
Okay. Well, I didn't expect that for you to see that at that point. So if you did, I misunderstood your question. But that's exactly what's going to happen.
yeah, because as soon as you put the cx plus d out, I thought it was going to be a system of equations.
So this is what we know so far, right? If you have a single equation and two unknowns, you cannot find a unique solution. However, we have a second piece of information that we haven't used. And we know that f of 2 is 41. So if I plug 2 into this, it should spit out 41. So 4 times 2 cubed minus 3 times 2 squared plus c times 2 plus d must be 41. And this is where I said there's no guarantees how pretty this is going to be. What's that? 8, 4, 32. 4 minus 12 plus 2c. c times 2 is 2c plus d is 41. Please, 10, 30, oh. Okay. So what's this going to be, 20? Subtract 20 on both sides, you'll get 21.
Divided by 2.
I'm not going to divide by 2. Look, this right here is 20. Subtract 20 on both sides, you get 2c plus d is 21. Yes? Two equations, two unknowns. That is a system of equations. And you did that in college algebra. So this is the way we write this in college algebra. You'd write something like this, a big brace. You go c plus d is 6. And then you put the other one in there. 2c plus d is 21. And then you have two common methods used to solve something like this. Elimination is one of them, and the other one is substitution. And it's your call. I like elimination. I especially like elimination right now because this is going to work out really nice. Elimination, what you do is you look at both your variables and you see what you could do to make them cancel. So I notice on my d's, if I just made that a negative d, they would cancel when I add straight down. So I multiply the entire first equation by -1. So I'm going to rewrite the system with negative c minus d equals -6. The negative has to pass through all of them, right? Right? Okay. Right. And now you can add straight down. When you add straight down, what do you get? C is 15. Ah, we have one of them. And now you can plug in 15 into any of the equations. Doesn't matter which one you go into now. So C is 15, and now what I'll do is I'll take that first equation. C plus D is 6, right? We knew that? I'll just replace C with 15. So 15 plus D is 6, so D is -11. There we go. What? Yeah, no, 9, sorry. Minus 9 though, right? Whew. All right, I'm ready to write the final answer. My final answer is that f of x equals 4x cubed minus 3x squared plus 15x minus 9. Double check, because I just did that out of my head. It was 4x cubed minus 3x squared. Then we had plus cx, but c is 15, and then plus d, but d is negative 9. There it is. There's your function.
Why'd you get 15?
How did I get 15? Oh, right here. Just add these straight down. So 2c take away c is c. Negative d and positive d cancel. This is why I multiply by negative 1. So these will go away. I get plus 0. Then equals negative 6 plus 21. That's 15. Sorry. That's called elimination. The other way is substitution, which I didn't show.
We can plug in your calculator.
Or you can, yeah, well, if it becomes a system like a larger system, then of course you want to be able to use your calculator. All right. Good?
Professor,
Yes.
question. Let's say, for instance, that this was like if we had to do, like, I don't know, this was like the fourth derivative, and they gave us a couple of points on the first derivative, would that still work?
Fourth derivative, they give you some points back from the
Original function.
original. Well, you answer that question. What do you think?
If it-
How many would you need?
I don't know.
Okay, so look, we have, in order for us to get from f double prime back to f prime,
We gotta get 2 points.
back to f, right? At each step I get a constant, right? So I'm going to get a constant there, and I'm going to get another constant there. So I'm going to have 2 unknowns when I get back to this. So you better give me 2 points. So if you want to look at it this way, if you want to start at f, proper notation is the 4 in parentheses. Back to the third, I'll do primes for that one. Back, then you're going to have 1 constant, 2 constants, 3 constants, 4 constants. I need 4 points.
So basically, the derivative of the number,
Yep.
determines how many points required.
How many points would be required to hopefully get it? We also need to keep in mind that not every system of equations has a unique solution. So there are some bigger issues in play here. But to answer your question, we would need more points. But we don't need usually to go past the second derivative. Because again, it applies more to real world, like, position, velocity, acceleration. So if someone tells me, hey, I drop a ball, right? And when I let it go, right? When I let it go, it's 200 feet off the ground. Right? And then they tell me that it takes 8 seconds for it to hit the ground. So I have a ball, drop it off a bridge, right? Like this. Up here, at time is 0, it's at 200 feet. And down here, when it hits, it's 8 seconds later, it's at 0 feet, right? So the x-coordinate is time, the y-coordinate is the height. So if I tell you that, then you should be able to tell me exactly where that ball was at every point in time, right? Yeah. Because you know the acceleration is gravity, and you have 2 position points. You have 2 pieces of information about its position. So just that alone, you should be able to tell me, okay, where was it at 1 second, at 2 seconds, at 1.356 seconds? All that information is available to you, but you have to be able to recover the position function. Got it? I think that's pretty powerful to be able to do that. All right, let's move on. We don't have a whole lot of time. There's only about 15 minutes, but I think we can start thinking about substitution again. Substitution.